Hi there, I'm Zach Morrell. I'm a postbac at Los Alamos National Laboratory, and today I'm going to be talking about quantum annealing in Julia. This is a project that I've worked on with my collaborators, Carlton Coffrin and Mark Fouffret. So, what is QuantumAnnealing.jl? QuantumAnnealing.jl is this software toolkit which came about as a result of some of the research which we've been doing at Los Alamos Labs, which we thought would be useful to provide to the community in order to hopefully be able to facilitate other people's research as well. So it's used for simulating quantum annealing as well as visualizing some of the dynamics which may be occurring within the system as well. So, who is QuantumAnnealing.jl actually for? It's really easy for me to just put all these very generic answers on the slide, but the real answer is it's for people who either want to learn about quantum annealing and continuous time quantum computing, or it's for people who actually use quantum annealing hardware in their research and they want to be able to model what's going on internal to that system. So before I can really start talking about what quantum annealing is, it's important that I provide a little bit of a basis for what quantum computing is. So I'm going to give a little bit of a lightning round introduction to what quantum computing actually is. There's two primary paradigms of quantum computing which most people are researching nowadays. There's the much more popular gate-based or circuit model quantum computing, where you assume that you're provided these unitary matrices which operate on your input state vector, which end up transforming it in rather predictable ways. You assume that the time dynamics are hidden and that you just have unitary matrices which behave exactly the way that you want them to. So on the bottom left here, I have an example of the very well-known quantum teleportation circuit, where you are using these unitary matrices to transport an input state from the first wire down to the third wire. Now what about the continuous time model? In the continuous time model, you're evolving a Hermitian operator with time, and this evolution is itself unitary, but the unitary is dependent on time. You don't make any assumptions about it performing a specific action. This would be more easily compared to analog classical computers, whereas the gate-based model is more analogous to gate-based classical computers. So that may be a little bit of an explanation for why the gate-based model is so much more popular, is because it just feels a lot more familiar. And in this figure that I show down on the bottom right, this is an example of how the instantaneous measurement probabilities of just an arbitrary system that I cooked up evolve over time when given a total evolution time of 100 nanoseconds. So, what kind of quantum computing hardwares are actually being realized nowadays? And the answer is both. So for the gate-based models, there are companies such as IBM who are producing these gate-based quantum computers using superconducting loops, using transmon qubits, and that's how they're doing their realization of gate-based quantum computing. On the other hand, we have companies like IonQ or research laboratories like Sandia National Labs who use ion trapping devices in order to make their realizations of gate-based quantum computations. So what about the continuous time model? Well, in the continuous time model, we have one of the biggest quantum computing companies out there today, D-Wave Quantum Computing, and they're making these hardware realizations of machines called quantum annealers. And those quantum annealers are what we're trying to model with the software package which we've created. Similarly, MIT Lincoln Labs, in collaboration with some other academic institutions such as the University of Southern California, have produced their own quantum annealing chip. So there's quite a bit of research being done on both sides of the quantum computing coin. So what kind of software is out there? Because you need to be able to model these systems in order to understand what you predict and whether or not your hardware is behaving the way that you expect it to. So for the gate-based model, we have software such as IBM's Qiskit, which they use for both submitting jobs to their quantum computers as well as simulating small quantum circuits. To bring it to a more of a Julia perspective, we have Quantum BFS's Yao.jl program, which is a very excellent program for performing gate-based simulations, but it's only operating in this unitary computing paradigm. So what about the continuous time model? So to bring it back to Python, there's the QTIP software, which is an open source software for simulating quantum systems. And similarly in Julia, there's the OpenQuantumTools.jl package from the University of Southern California, which is an excellent package for simulating the open dynamics of quantum systems. Lastly, we have LANL's QuantumAnnealing.jl package, which is more specialized for actually working with the quantum hardware which we've been doing our research on. So each of these is an option, and there are also several more packages which I haven't listed on these slides. So it's a better idea to start with why quantum computers before explaining how quantum computers. So why are we interested in researching quantum computers, either hardware or software? And the answer is because simulating these quantum computers and just quantum systems in general is quite hard to do on a classical computer. The problem difficulty scales exponentially with system size, and the reason for this will become quite apparent later on in this talk. So the other big reason beyond just simulating quantum systems is that by doing these computations on a quantum computer, we can solve certain problems much more quickly than we can classically. So as a few examples of this, I have on the left side the very famous Shor's fast factoring algorithm, which is able to greatly speed up factoring of large semi-prime numbers, at least in theory. This turns out to be very difficult to practically realize, and we're not currently capable of performing this algorithm on any of the current quantum computers that are out there. But someday in the future, we may be able to actually do this, and that would have some very large impacts for fields such as cryptography. What about the continuous time domain, though, you may ask? So on the right side, I'm showing the welded or glued trees problem, where you say I'm starting in this entrance node, I'm trying to get to the exit node, and I have all of the nodes in between assigned random labels, and I'm only able to see the adjacency matrix to each of these nodes that I'm at. It turns out that in both gate-based and continuous time quantum computing, you're able to get an exponential speed up on this problem as well. For a much more complete list of algorithms where you're able to expect a quantum speedup, you can look at this website quantumalgorithmzoo.org, which I've listed at the bottom of this slide. So what actually is a qubit? The easiest way to conceptualize it is you can think of it as a unit vector on a sphere. And the way that you figure out what your probabilities of measuring a certain state are is by performing a projection onto the vector that you're trying to compute the probability with. So usually what we're working with is the computational basis, which uses the eigenvectors of the Pauli Z matrix. So I have the Pauli matrices shown here, the Pauli X, which often ends up performing similar to a NOT gate on a quantum computer, the Pauli Y, which is a little bit harder to conceptualize, and then the Pauli Z, which is quite often what we're measuring on. So the Pauli Z matrix has these two eigenvectors, 1, 0, and 0, 1, with eigenvalues +1 and -1, respectively. And that ends up bringing up the notation that I have for certain measurements. So If I say that we measure a 0 or a +1 or a spin up, that all means the same thing in this context. And similarly, if I say that we measure a 1 or a -1 or a spin down, that also ends up meaning the same thing. And this vector can be a linear combination of these two basis vectors, but this linear combination needs to have unit length, so overall magnitude, like length 1. So how does this end up scaling up, though, to multiple qubits? The answer is that it scales using something called the tensor product, or if you're applying it to matrices, the Kronecker product. For simplicity, I'll just refer to it as the Kronecker product, and because it ends up behaving in a similar manner for both vectors and matrices. So the Kronecker product is described as shown in this image on the top left, but effectively what it ends up meaning is that every time you add a new qubit to your system size is doubling. And this is why your system's representation is scaling exponentially, and that's why it's so hard to simulate on a classical computer. So what actually is quantum annealing? It's this thing that I've been talking about this entire talk sort of nebulously, and it's finally time that I say what I'm actually meaning. Quantum annealing is simply a combinatorial optimization problem which is meant to be run on a continuous time quantum computer. So what quantum annealing aims to do is to minimize the energy of some target function encoded as a Hermitian operator called a Hamiltonian. So what I'm showing here is you start with your initial easy to prepare ground state, and then you slowly change your system until you are in the ground state of your target Hamiltonian. And ideally, if you go slowly enough, you should be able to stay in the ground state and get a good solution out. So one of the most common target Hamiltonians that people like to use is something called the Ising model. So shown below, I have the classical Ising model, where you say I have certain biases on each of these bits, or usually we call them spins because we assume that they have value either +1 or -1. And then we have coupling strengths between these bits. And these couplings can be either inclined to agree with each other or disagree with each other. If they agree with each other, we call those ferromagnetically aligned. And if they disagree with each other, we call them antiferromagnetically aligned. So if we just get rid of these HI terms and only look at the JIJ terms, what you might be able to realize is that if we have positive JIJs, or just 1 values, on a certain graph, minimizing this function will actually correspond directly to performing a max cut, because we are assigning -1 and +1 values to each of the bits. We're effectively ending up with a maximization of the cut as we minimize the energy of this function. And that's an NP-complete problem. So one big question that people might actually have is, do we expect to be able to solve NP-complete problems with a quantum annealer? And unfortunately, the answer is no, at least not with an expected speed up that's exponential. So, however, we might still be able to get a overall improvement compared to classical algorithms in terms of perhaps approximation. That's currently an active area of research. So how does this all actually work under the hood? The answer is it's relying on something called the adiabatic theorem. The adiabatic theorem says that if you start in a ground state of a known Hamiltonian, and then you evolve the Hamiltonian through time for a long enough time period, you will eventually end up in the ground state of your final Hamiltonian. And depending on what your annealing schedule is, this can actually change the total amount of annealing time that you need in order to end up in this ground state. So what's an annealing schedule then? An annealing schedule is this A of S and B of S function which dictate the strengths of your input and target Hamiltonians. So at the start, you want to have the magnitude of your A function be much more significant than the magnitude of your B function. And at the end, you want the magnitude of your B function, corresponding to your target Hamiltonian, to be much stronger than the strength of your A function, corresponding to your input Hamiltonian. These schedules can have many different forms. Here I'm showing the linear annealing schedule and a quadratic annealing schedule, both of which are quite popular to use within the literature. But unfortunately, when it comes to real-world hardware, quite often these annealing schedules aren't actually as simple as they end up appearing in the literature. So what we can see is usually academics like to use the linear annealing schedule for estimating how a system will behave. But when we actually consider what's occurring on a quantum device, we have these much nastier expressions, which here we're simply modeling with a quadratic and a piecewise quadratic function. However, on the actual hardware, you end up just getting CSV files corresponding to strengths at different points in your annealing schedules. And these are completely machine dependent. So these vary from piece of hardware to piece of hardware. And for that reason, it's really important that we're able to actually model what's going on real hardware, because it doesn't correspond necessarily as straightforwardly to what we see in the literature as we might like. So, speaking of quantum annealing hardware, how is this actually realized in the real world? So the most prolific quantum annealer is produced by a company called D-Wave Quantum Computers. And they're attempting to solve the transverse field Ising Hamiltonian with their quantum annealer. So when I say the transverse field Ising Hamiltonian, it's that same Ising model from earlier as our target Hamiltonian. And then for our initial Hamiltonian, we have this sigma ix term, or the transverse field term. And this has a very easily prepared ground state, which is just the uniform superposition state. And if you're not very familiar with how quantum mechanics works, you can think of the uniform superposition state as effectively being this prepared state where when you perform a measurement, you have an equal probability of observing every single value in your system. So mathematically, the way that this is actually realized is shown down below for the sigma xi and sigma zi terms, because it can be a little bit confusing to realize that these are actually 2 to the n by 2 to the n matrices that you're working with. So, and when we perform our measurements, we're measuring either a +1 or a -1 because we're measuring on the z basis. On the right side over here, I have one of the connectivity graphs of one of D-Wave's current quantum computers. They call this connectivity graph a Pegasus graph. Here we have a 4x4 set of unit cells, and it effectively ends up breaking down to a few K44 bipartite graphs, which are all connected to each other in the manner shown below. So we're not actually quite often able to realize a fully connected graph, so there's some embedding problems which end up needing to be solved as well. So, okay, we have this quantum annealing algorithm. How does it compare to the much more well-known thermal annealing algorithm, oftentimes called simulated annealing? They actually produce very different results. Thermal annealing, you basically say, I'm going to start with a system at high temperature, and then I'm going to cool it, cool it, cool it, and then finally sample from the distribution after I've cooled, and I should sample from a Gibbs distribution, meaning that with high probability I should get a ground state for my system. Quantum annealing ends up producing entirely different results because of the way that the dynamics end up working out in the Schrodinger equation. It's not immediately intuitive why this might be the case, and it does require a little bit of effort in order to explain, and I unfortunately don't have time to discuss it in this talk, but I will show some of the effects later on. So I have these two different models. one of them has 6 degenerate ground states, and one of them has 17 degenerate ground states. And the way that they perform between simulated annealing and quantum annealing is actually quite different. So in the case of the 6 ground state model, we have the simulated annealing effectively reproducing a Gibbs distribution. So we sample each of these different ground states with nearly equal probability. Whereas in the quantum annealing case, if we evolve our system long enough, we end up having 2 of these ground states be massively suppressed compared to the other ground states. So we get completely different measurement distributions depending on which algorithm we use. And it should be noted that in certain cases, such as this 17 ground state model, we can actually observe an amplification in some of the probabilities. So thermal annealing doesn't actually produce a direct Gibbs distribution, because if this were a Gibbs distribution, all of the ground states would have equal probability. But similarly, quantum annealing doesn't either. It ends up suppressing one of these ground states to the point where we would never really expect to observe it in a completely closed system. If this system were open, we might observe something else, but that's beyond the scope of this talk. So what do I mean when I'm saying that we're simulating a closed system? So a closed system, in a quantum sense, is simply evolving according to the Schrodinger equation, which is shown down below. You can also represent this through something called the Liouville-von Neumann equation, where you're modeling density matrices, where you define your density matrix as the outer product of your state vector with itself. Or you could also be able to model your dynamic simulation through unitary evolutions, where you say, I'm going to figure out what unitary matrix ends up producing the transformation with time. So your time-dependent unitary. So for open system simulations, there's much nastier equations, and we don't have any support for that currently in QuantumAnnealing.jl, and I recommend that if you're interested in doing those kinds of simulations, that you use OpenQuantumTools.jl. I haven't shown any of the equations for that down below because they're overall really nasty, and I feel like they would possibly scare some people away from this talk. So what exactly is QuantumAnnealing.jl doing? So we're simulating the closed system dynamics, and the way that we're doing this is through something called the Magnus expansion. So a Magnus expansion aims to get a very good approximation to these unitary transformations by breaking our anneal into several individual steps and then approximating the unitary for each of these little steps and then multiplying them all together. The big benefit to this is that you end up preserving your probability distribution in your quantum state vector, even if you have slight errors in your computation. So we also include a wrapper for differential-equations.jl, but we don't quite prefer this method as much because if you don't have your tolerances set to be low enough, you can end up having issues where you do your anneal, and then at the final state, you're no longer actually in a probability distribution, which can have some really nasty effects on some of the algorithms that you might want to run to evaluate your final quantum system. So what are some of the features of this QuantumAnnealing.jl package that we've written? So one big feature, and probably its largest selling point, is how simple the code is to write. So here I've shown that in 7 lines, including just using statements even, which I don't know if you can even include as like a line of your code, you're able to produce these plots of both what your icing model looks like and what your output state probabilities end up looking like with a given annealing time. If we exclude the plotting and the using statements, this is only 4 lines of code in order to perform a quantum simulation. So we also have our simulator automatically tuning itself in order to get the final measurement probability within a certain amount of error as well. So you don't need to do a lot of fiddling on your own with these error tolerances, which is in my opinion, a really big feature of this code. So what else do we have in here? We have a bunch of different annealing schedules which you can use out of the box, including the very well explored linear annealing schedule, quadratic annealing schedule, something which we've found has some really nice effects called the circular annealing schedule. And then we also include a D-wave-like annealing schedule where we've interpolated over a D-wave annealing schedule using a quadratic piecewise function. But it should also be noted that we have capabilities for reading in these CSV files and interpolating through a quadratic spline. Alternatively, you can make your own annealing schedules if you're trying to research how your annealing schedule may impact your measurement probabilities in a certain problem. What else do we have? We have the functionality for plotting your icing models, which you input. And this can be overall really beneficial for figuring out how your problem structure actually looks for much larger problem instances, and it can help you sort of conceptualize what parts of your system you expect to contribute more to your final measurement probabilities than other parts. We also have the ability to directly process D-Wave runs using some other tools which we've developed here at LANL. So we have this BQP JSON format, which represents the output from a D-Wave run and then stores it on your computer so that you can evaluate it later. And using this QuantumAnnealing.jl package, you can read in this format and directly display what you're actually getting from the D-Wave hardware. We also have a D-Wave instance generator where we generate these different problem instances which you can submit directly to a quantum computer using this DWISC software shown below, and you can simulate these same instances directly through QuantumAnnealing.jl. So you can have a direct one-to-one simulation to job submission, making it so that you're able to not have to rewrite nearly as much stuff. So what else do we have? Instantaneous ground state plotting. So if you give an overall total time for an anneal, we have the capability to say, okay, at a certain point within our anneal, if we were able to measure right now, what would we expect to see? And this can vary quite extremely throughout the course of these anneals. So on actual physical hardware right now, specifically the D-Wave machines, you can't perform instantaneous measurements. You can only perform measurements when S is equal to 1. But if in the future you're allowed to do this, this would be a very nice capability, so we've included it for now. We also have these time-varied state plots. So this is where you say, okay, I'm assuming that I can only perform my measurement at S is equal to 1, but I want to see how my measurement probabilities will change if I change my annealing times. And this can be quite a large impact, so we include that as well. So how does this end up performing against the differential equation implementation that we have? So our Magnus expansion is actually significantly faster. So this may be coming down to certain naiveties in our programming. This is still a rather young software package, so there may be some inefficiencies. But for example, in this 5-qubit case on a fully connected graph, we're getting about a 20 times speed improvement. So what should I use between Open Quantum Tools and QuantumAnnealing.jl? If you're doing open quantum simulations or you're working with very complex Hamiltonians, I recommend that you use OpenQuantumTools.jl. It's currently a much more complete package for stuff like that. But if you're working with hardware annealing schedules and you want to be able to feed that to Open Quantum Tools, you could honestly use both QuantumAnnealing.jl and OpenQuantumTools.jl. And if you're trying to do much more rapid prototyping or you're working with long annealing times, then QuantumAnnealing.jl ends up being a little bit more convenient of a tool because it automatically tunes its errors and it's has the guaranteed built-in probability preserving properties. So hopefully in the future we can do a little bit better code optimization on our package, We also want to see what people actually want to have implemented. We are trying to keep this package relatively lean for now, but if people have something that they think would be useful in their research, please feel free to reach out. So overall, these are the contributions of our software package. We've got something which is really useful for fast prototyping and for modeling what's behaving on hardware implementations, and it's something that has really been useful for our research, and we hope that it can be useful for other people's research. The GitHub links are down below, and with that, any questions? Thank you.